Okay, so what have we learned on gradient descent so far in this course? Anyone? So in the last, or we were knowing by just taking one example that where you should move so as to minimize your function. Where you should move? What's the direction you have to move in order to minimize any function or optimize any function? Gradient, or in the negative gradient direction. If you move according to the direction of the gradient, increase. The function value will increase. That's what we saw in like last example. Okay. So yeah. So this is so we learned about the one-dimensional gradient descent method. Okay, what does it tell us? That you have to move. There are two you have to move. Okay. So the minimization is here. Suppose the calculator is the point where your minimization of the function lies. So how should I move? Should I move? I should go straightly there. I should go straightly there. Shall I go like this? Shall I go like this? No, that is inefficient. That is inefficient, right? If I go like this, it's inefficient. Rather, this is the shortest distance I can go. So this is exactly what gradient descent is doing. Exactly. And we learned the simplest example of gradient descent last class. That is one-dimensional. Sure, like, okay, I'm not able to do it. So I think this was one of the examples. So this was the example where I showed you that you have to go opposite to the gradient in order to minimize the function. Okay. Then we discussed one-dimensional gradient descent. So I told you, see this one. I told you that one-dimensional gradient descent looks like this. So you have to change the value of x by introducing this eta and f prime of x for 1D, one dimension. So eta is the step size in numerical methods, but when you deep learning and the neural network concepts or neural network class, this will be nothing but learning rate. This eta will be nothing but learning rate. Okay. And this f prime of x is the derivative. Fine. Now I asked you a simple question last class, and this statement you only told me that if I go to n dimensions, how the gradient descent looks like. So you told yes, this x will now be a vector. This x will now be a vector because here it was a value vector because it is in n dimensions. Fine. And here also you have learning rate eta. Okay, but instead of derivative f prime of x, you will now have gradient because that's what the generalization of derivative. So therefore f prime of x is played by the role of gradient of x. So this is what n-dimensional gradient descent looks like, or multivariate gradient descent looks like. Okay. Of course, this is a vague way of saying it. You it. How we prove this quantity? How we prove this? Series expansion, right? Last class, if you remember, expansion. This is the Taylor series expansion. Expansion. So if you want now to derive a gradient descent method for n dimensions or multivariate, expand Taylor series in multi dimensions, like n dimensions. So that is out of the scope. Like you can know about it, we can prove, but I'm not going to prove it because you just got an idea how to expand Taylor series and get how to derive gradient descent in simple case. ND. If you want to go to ND, you can do the simple Same Taylor series expansion in n dimensions, in n variables. Okay, that is a bit difficult. It is in my notes. It is in my notes. Okay, but you can see it. So yeah, this is what it is, and yeah, I think in a Python example, one more case, Python collab notebook like. Consider this two-dimension function. So we are taking very simple looking, very nice looking examples. Why are we taking nice looking examples in the first place? That's my question to you. Because these are the best toy examples you can take to understand these concepts. The idea is to solve complicated problems, but that's what we are not doing in this class. We are taking simple toy example, minimal work. This is the case, okay? And yes, you can apply that to any other cases, any other complicated cases. Like first example, to minimize this, answer is median. The answer is median. Okay, because I saw class about mean, and then I gave you this assignment telling that yes, the number of positives and number of negatives should balance, and that's what median does. This is where you can see a connection between analytics data and your optimization. Okay? So this function is simple enough, but learning it, because this function will simply look like a v function, and you can find the derivative or whatnot. Okay, learning it. You might never see this modulus function ever again. Complicated like this. How many of you think it is differentiable? How many of you think it is differentiable? Non-differentiable. Mr. Chakko, why you think it is non-differentiable? Right, but you have to tell it in a proper way. Yes. So Mr. Chakko was saying that it is not looking like this. Like this. Okay. So why? What is the difference between this and this? The difference is sharp points, some kinks. So mountain top. Okay. So mountain tops are not differentiable because here you can find any gradient. Any gradient you take, it will make you realize that yes, it can be a slope. But any other thing you take, it won't happen. Okay. But here, many possible cases are there for the slope. Okay. So therefore, this is one geometric interpretation why it is not different. So these might be the cases. These might be the cases. Okay. Okay. So if you take this function, so is it a multidimensional function? Yes, because it has two variables x1 and x2. Can we compute the gradient of f? What is gradient of f? To x2. Done. What should it be? X1 plus 0, 0 plus 4x2. So suppose we take the initial condition -5 -2 and we apply the gradient descent what we learned so far, that is x bar, that is x bar is x1 x2. So we want to apply multivariate gradient descent. X1 x2 at the k+1th iteration, 1 th 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 x1 k, x2 k minus the learning rate or the step size multiplied with the gradient, that is 2x1k x2k from 1 from 1 from 1. Okay, so if you visualize this, okay, if you visualize this, we'll visualize this in Python. Okay, so you will see that when eta, the learning rate is taken to be, the step size or learning rate is taken to be 0.1, okay, and the initial condition is -5, -2, after 20 iterations, it converges to the minima. How the minima should look like? Any ideas? What should be the minima? What should be the value? Just an idea, like you can just visualize that it is x1 square plus some 2x2 square. So it should look like a paraboloid, right? It should look like a 2D version of a paraboloid. So a paraboloid, what should be the minimum? 0, 0. Parabola 0 is the minimum. So in paraboloid, you have two variables. So 0, 0 should be minimum. So you'll see that yes, 0, 0 is the minimum and 20 needed. You'll see that in Python. Okay. I think so. X approaches its minimum 0, 0, but the approach is very slow because you are taking 20 iterations. Okay, so gradient descent, this shows that gradient descent is not all in all. Gradient descent is not all in all. There exist methods which are much better than gradient descent. Okay, and that's how the evolution of optimization algorithm has taken place. So this will be the evolution in this course. The evolution can be generalized into multivariate gradient descent faster than multivariate gradient descent is something known as stochastic gradient descent. Stochastic gradient descent, why the word stochastic has come, I will just give you a bit of motivation. You always know that any optimization algorithm might work, but it might get stuck to a local minimum, which you don't deserve. That's what most of the deep learning problems face. Okay, because deep learning problems are high dimensional, okay, multidimensional, and there are a lot of parameters. When you optimize, it might get stuck into a local minimum. The training error might get stuck into a local minimum, but you don't want that. You want to much more less than that. Okay, but your method, whatever you are using, how many times you run, it will always get stuck there. So in order to kick it out of that stuckness, if some ball is stuck, if something is stuck, what you do? If something is stuck, what you do? You just try to hit it, right? I hope in your rooms, when you clean your rooms, dust is there. What you do to clean your room? You take a broomstick and clean it. But what actually you are doing? The dust is lying there. You are actually kicking the dust. You are actually kicking the dust away from its position. Same idea is being used here. Same very idea is used here in stochastic gradient. That using the stochasticity, using the noise, using just the noise. So that's what stochastic gradient does. But the main trouble of stochastic gradient descent is it will be slow. It will be slow because every step you will see, every iteration we have to do something. I will tell you that. Due to that, something new. We have to do something more. What we have to do something more? So to achieve their goal, okay, because you know deep learning has learning problems can not work in GPU. Okay, they have to work in GPU. Like you have to parallelize your jobs into multiple GPUs. Okay. So you are giving a chunk of each of the job to each GPU to work it. Okay. So therefore, this is the new idea came. That is, you have to batch. You have into batches. You have to batches and give it to each of them. That's what you do function, isn't it? That's what your seniors did while organizing technical fest, tech fest. They gave all the seniors met and each work and each one is doing those works. That's how successful the event was. Yes, if only one person or two-person were doing it, it won't be successful. So you have to divide the work. That's exactly what they did. Like they are separating into batches. This gave me this idea. This gave me this idea. Okay. This gave me the idea that it is known as mini batch. You have to divide the work into mini batches and give it to GPU. Okay. Mini batch gradient disk, mini batch stochastic gradient disk. So here I will show you through matrix multiplication actually just this is our toy example in this class. Show you matrix multiplication, whatever you have been doing so far, were you doing the fastest method or were you doing the slowest method? Okay. So we will calculate the time, how much Python is taking just to multiply two matrices and how we can reduce the time to 1 by 10th by doing some. That will give you an idea of mini batch stochastic gradients. Okay. After this, we will come to the deep learning era. Deep learning era where Python has inbuilt optimizers in it. That is, we will try to talk about. We'll try to talk about AdaGrad optimizer. Okay, we'll try to talk Adam optimizer. Try to talk about RMS prop. Okay, of course, try to see if time permits scheduling. So this is where the optimization part will end. The optimization part will end. Okay, I hope you will let me cover till this. Okay, this is what I want you guys to learn. Of course. So I will tell you what we are planning in this course. Okay. So this is the optimization part. This is the optimization part we will cover. After that, we'll come to regression, numerical regression. How and how regression is related to multi-layer perceptron and all those things. Can be connected to numerical methods. Okay, you can actually use neural networks to solve differentiation. You can actually use neural network to solve integrations. That is what is known as PINN, physics networks. Okay, but we will not cover in this course. Maybe for future students. Okay, that is neural networks. Then done. We will go to PDE. There we will learn only one method, that is some boundary method. Okay, some boundary method. You have to the average of 4 coordinates. I hope some of you have already read in your bachelor's. Okay. Yeah. So that will be the end of this course. Okay. So after, so these, yeah, from every, you can expect one or two questions for your exam. So that's what will be the end of this course. Okay. So since you were learning only the, So you would not have learned much of the things. Okay, so therefore I merged numerical optimization into numerical method, which is also in your syllabus. Okay, so therefore we are learning something extra out of it. Right. So yeah. So what is stochastic? Yeah, we will learn the Python example. That's what we were planning. Yes, you can see this function here. So can you see the objective function x1 square plus 2x2 square that is defined on the first line over here? Then I'm taking the gradient of it. So 2x1, 4x2. Okay. So what I am doing here, I am applying the gradient descent, simple gradient descent. No stochastics is involved. Okay. So you can see x1 minus eta times gradient 1, x2 minus eta times gradient 2. Okay. Fine. All good. Okay, so what we are doing next is kind of training it. You can see it here. So number of steps. Have I defined the number of steps here? So how many steps you have to define? So I think above it might be there. Uh, Somewhere I have defined, but maybe you can take like we have taken 20 steps. Okay, we have taken 20 steps and here we are training it. Here we are training it. Okay, so that's what number of iterations. Like you have to one iteration, then next iteration, third iteration. That's what numerical method is about, right? You have to iterate your methods again and again so as to approach the solution. In you exactly do the same. You are going, that is known as forward propagation and backward propagation, so as to more like polish your outputs. Okay, to more polish your outputs. Fine. So this is where methods start to develop. You can see I am taking the initial guess as -5, -2 here, x1, x2. And I am storing results, all the results in a list that is results. Okay. And for you can see that I'm using the trainer function and I am iterating it again and again. Plotting, then all about plotting. So this is what it shows. This is what it shows. You can see that we have plane. We have taken x1, x2 plane, and you can see 0, 0. Can you see where 0, 0 is? You can see here, exactly here. So you can see we started from -5 and -2, isn't it? We started from -5 and -2. Then gradient descent took us here, then here, then here, and it is slowly approaching here. But what is speciality about that point? The speciality about that point is it is approaching 0, 0. That means it is the local minimum. Okay, or whatever, it's a minimum, it's an optimal solution. Okay, so you can see gradient descent is working very nice, but the only drawback is it is taking more steps, 20 more than 20 around steps. Okay, so therefore gradient descent is kind of slow. Now how we can optimize it? We don't want slow, we want to make it more fast. Okay, so there stochastic gradient comes in. So yeah, so this is all about Newton method I have shown you. Yeah, we'll analyze this. We'll analyze which is better, whether it is stochastic gradient or gradient. Okay, that comes later. But yeah, we'll learn about stochastic gradient. Okay, let us come back. Fine. So in stochastic gradient, actually in deep learning, actually, they are not about stochastic gradient. Actually, in deep learning, when you take an objective function, what is your objective function? Basically, in deep objective function is usually the training error, and it looks like this. It looks like this. So, so you, so after this class, after this class, you tell the technician that this is not working. If I try to zoom, it is not working. So I don't know. Yes, you can see here. Okay, you can see here. This is what I am doing is I am trying to find the network weights that achieve the lowest loss. Okay, lowest loss means, yeah, I told you that learning, the loss you face in deep learning. Okay, the output is something else, but you try to reach to that to reach to that output. If you don't reach to that output, there will be some error. And that's like a training error. Okay. As you do lot of epochs, it's likely that your training error will decrease, but there is a cap where after you decrease even the number of epoch, still the training error won't decrease. It will behave erratically. There is a margin where it will happen like in a good way. Okay, but not always. That we will learn in deep. That this is the case where we are finding the weights. So we are taking the loss function. This is the loss function. Don't need to worry about too much of each of these. Just, just understand that this is a function and weight vectors of your neural network. That's it. Nothing more. So depending on that, you are getting the loss function. Nothing else. Okay. And this is the function L, which is the loss function. And training samples. So you are summing it over n samples. So you will obviously have more than one sample. One sample. So you are taking it for n training samples. So we are taking the average by 1 by n of that loss, and we are trying to minimize that loss. Okay, we are trying to minimize that loss. Plot it. When you plot it, it gives you something like this. It gives you something like this. Okay, you can see the loss function j. This is the loss function actually j. So this whole thing I can write it as j of r. Okay. So this is depending on the weights. W0, W1 are the weights. And you can see that J of W0 architecture, how the loss is varying. So this is the plot, this is the heat map, surface kind of heat map. And actually, the maximum of that heat map will give you the where it maximum loss is achieved. And the bottom part of the surface or the weight combination where minimal loss is achieved. That's clearly visible. Yes. So your job is to go some you want. So I started from here. Suppose I started from here. This is the surface. This is step number one. You take the initial guess. Take the initial guess. That is denoted by this sign. What is that sign representing? About it. Think about it. Okay. So you know to opposite to that direction. Okay. So the arrow is giving here, but he is going opposite direction. Okay. You can see that's the step 3. Slowly see that the values are decreasing. Then you keep on decreasing the values like here. Is that something special? Yes, it is something special because that's where the minimum is. Okay, so you can see a picture how optimization is actually achieved or optimization algorithms are actually used in your Python libraries. So this was just a motivation for you. Anyway, we'll come to our main thing. Learn about stochastic gradient descent. And before that, like in deep learning, actually, when you're taking the objective function, you just saw that we are taking the average of the loss function for each example in the training data set. That's what you exactly saw. Because you saw we took the n training samples and we were averaging it for all the losses. Okay. So in deep learning, you do that usually. And that is equal to the average of the loss functions for each example, or you can see it as a sample, okay, in the training set, the training data set. Okay. Fine. So therefore, given a training data set of n example, so let me write some notations here. So we are given a training data. These are given quantities. We are given a training data set of n examples and we assume that fix bar, it's a multidimensional problem. Fix bar is the loss function. Is the loss function So for training example I, for ith sample, you have the loss function fix. Okay. Fine. So therefore, you can see like the total loss. This is the loss or the objective function. The objective function is given by f of x bar, that is equal to the sum of each losses, on the training samples. How many training samples you have? Summing of the loss for all the training samples. So what we have to do, take the summation. Take the summation from I equal to 1 to n. And I told you that we have to take the average. You have to take. So this is your f of x. This is the objective function you want to minimize because this is the loss function you want to minimize. Okay. Fine. So can you tell me what should be the gradient here? Can you tell me what should be the gradient here? So gradient at x. Gradient at x bar is equal to grad f x is anyone? So what you can do, you can take grade of this quantity, grade of 1 by n summation fi, but that is same as 1 by n summation of grad fi of x bar, isn't it? I equal to 1 to n. Because gradient, think of gradient as differentiation. Think of gradient as differentiation. What would have happened if you would have d by dx here? You would have taken it inside, right? So that's what we are doing here. Miss Pooja, you are fine? It's fine for you? Fine. So if gradient descent is used in this case, can you tell me if gradient descent is used? Suppose if gradient descent is used, what should be the computational cost? So the gradient descent is slow. So there should be a computational cost in a good way. Okay. So the computational cost should be order of n. Why it should be order of n? Because you are computing this gradient, and in order to compute this gradient, these n number of iterations, summations. You have to do these n number of summations. So therefore, n number of operations are used. Therefore, time complexity or computational complexity is order of n. Fine? Okay with everyone? Mr. Rohit, okay. Okay. So when the training sample is higher, so when the training data set is high, when the sorry, when the size actually doesn't, yeah, when the size of the training data set higher, is that a problem? Size of the training data set is higher, is that a problem? Yes, because it is growing. The computational cost is growing order of n. So if you take a million of data sets, it will take million of that gradient descent will be slower because it is moving order of n. It is larger or larger size, the cost of gradient descent for each iteration will be higher. Okay. So therefore, stochastic gradient descent is introduced because stochastic gradient descent reduces the computational cost at each iteration. Okay. So when you take stochastic gradient descent reduces the computational cost. Okay. So actually the idea is pretty simple in stochastic gradient descent. Idea is like this. Yes. So for each iteration of the stochastic gradient descent, we actually uniformly sample from I equals to 1 to n. Okay. So there are n samples you have, n training samples, I equal to 1 to n. These are the n training samples. Stochastic gradient is like you take randomly from either of once at each iteration, you take randomly from each samples. You understood? You understood. Previously, what we were doing? Previously, all of them, I equal to 1 to n. In descent, the idea is you take one of them randomly from the training data set at each iteration. At each iteration, you take one of them. You got the difference between between these two in between gradient descent and stochastic. So that's what we are doing. Whatever I told you, I am writing it mathematically. Okay. So what should I write? Anyone? So at each iteration of stochastic gradient descent, now onwards I will write SGD, stochastic gradient descent. Sample, like uniformly sample. We uniformly sample an index I from this set 1 to up to n. Okay. Numbers here each represent the training data set sample. Each represent the training data set sample. Okay. Fine. So out of this, we select a particular index I at random for each iteration. For each iteration. Okay. So can you tell me what the new gradient descent look like? How the new gradient descent should look like? If instead of all of them, you only told me that instead of all of them, you just take randomly one of the sample out of the n. So how it should look like? So when you compute the gradient, shall you compute the gradient of all of them? No, gradient of that one only. So how it should look? Science, you have to write in gradient descent form. That's what I want from you. Water. Yeah. Kindly, Arshida, water. Anyone else thirsty? Okay, so how we shall update? How we shall update? Very simple. Why it is so lagging? It's simple. I'll give you one more minute. See the gradient method, what you wrote in your notebook just before. Gradient, multivariate gradient descent. Grad f is written, right? That you are doing for all the training samples. Now I told you that instead of all the training samples, you have to take one training sample at random and compute the gradient. So how should the formula look like? Instead of grad f, what you should have? Grad f, yes. Finish. Why it is taking so much time? Okay, anyway, so after this you compute. So select, you have selected, yes. So compute the grad, compute the gradient. Compute the gradient. How it should look like grad fi at x bar. Grad fi at x bar. That's what we were doing. You have f1, f of each training sample, and we summed it up, took the average, isn't it? Randomly one of them. So ith, suppose ith I am taking random. So that ith sample I have to take the gradient. That is what grad fix mean. Yes. So now it should look like x bar equals to x bar minus training learning rate or step size times grad fi x bar. Finish. Previously x bar equal to x bar minus eta grad f x. Grad f x was equal to 1 over n summation of grad fi at x bar. I equal to 1 to n. Can you see the difference? Able to see the difference? Okay, now observe the computational cost at each iteration. Computational cost at each iteration. Now, order 1. Order 1. Why order 1? No. Previously you were taking here you are taking the summation order n. Here just one variable is there. So it is order 1. Isn't it? Yes. So can you see which one is easier? Take gradient descent, it is order n computational load. Okay. If you take stochastic gradient descent, because you are introducing why it is stochastic gradient descent. Because we are choosing out of n random samples randomly, right? One sample you choose randomly out of that n. Yes, that's gradient descent. That's what you tell it to be stochastic gradient descent. So it is order 1. Now you can see at every iteration you take, what you will do for I equals to 1, 2 steps. And steps. For each number of steps, each sample out of the n samples. Now there are two conditions. Have you learned in data analytics sampling without replacement and sampling? Learned it. Is it? Now you should have asked me the question that here you said that take ith sample out of those n samples randomly. But should I do it with replacement or without replacement? I can take that sample and keep it with me. And in the next run, not participate that sample in that n, right? So you have n minus 1 samples. You have taken that sample for training put back in with replacement and again consider. It might be that that sample again be chosen. Okay. So which one is better? Better because each of one is better according to their own, according to their own, according to their own need. Please. Yes. So okay, so what we can do is like this is the stochastic gradient descent you are learning here. So we will compare. Like now you saw that it is order of one. Okay, at each iteration, the order of n, which is the normal gradient descent. So you can see that SGD is faster than gradient descent. SGD we saw that it is order of one quantity, whereas in gradient descent you see it is order of n. Okay, so like that, it is 1 by nth faster. So how many data sets you choose? Still at each iteration, it will be order of one quantity, due to which stochastic gradient descent is faster. So now what we can do is we will just take, we'll take one example here in Python, and let's see. So you can see here, yeah, this example shows for yeah, this example shows you this objective function theta minus x whole square. So it is kind of like regression error you are trying to look into here. Theta minus x whole square, and you are taking the mean of it. So it is the objective function. Then you are taking the gradient, that is the differentiation of that. So it is 2 times theta minus x. Okay, fine. But here the x we are taking is randomness. We are adding some variance to it. Okay, we are adding the mean to be 5, variance to be 4. Nothing special. It can be any other number. Okay, but why we are taking it? For one purpose. What is the purpose? To add stochasticity into the gradient descent. Stochastic gradient descent is much faster than gradient descent. Okay. Number of iterations is 50. And here I am a gradient descent example, whatever you have learned so far. Okay. So you can see that minus eta times the gradient. Okay, fine. So basically we are trying to compare. There are two things. One is the gradient descent on the first function I showed. This is the function for stochastic gradient descent. You can see that eta and stochastic gradient. So that x you will take is random. Okay. So to store all of this in GD history and SGD history. Okay. Like a list, we want to store all the values in a list, and we want to plot it to see how which faster. So these are all the plotting tools. Yeah. So you can see that this is how it is. Like you can see that gradient descent converges very nicely. Gradient descent converges very nicely. But stochastic gradient descent, come to the first bench. Why are you laughing? Without anything.